Hi guys, hope you all are doing well, and I also hope that your studies are going pretty well. So, yesterday was a very short video for Mayer's equation. If you have followed that, it's good. Otherwise, you can just go back and have a go through again for that video. Today we are about to study some different forms of kinetic energy for a gas. As you can see on the screen, there are total 5 formats of kinetic energy. There are total 5, and the first is the kinetic energy of a plain gas, just a gas. What is the kinetic energy of a gas? So if you remember, we had completed one of the very long derivations for pressure acted by an ideal gas, which says P, that is pressure, is equal to 1 upon 3 rho CRMS squared, where rho is the density and CRMS is the RMS velocity and P stands for pressure. Now, as we all know, density is equal to mass upon volume. We just replace density as mass upon volume. Then this 3 and this V is taken on this side, so that becomes 3PV equal to m CRMS squared. Now, if I want to find out the kinetic energy, the basic formula for kinetic energy is half mv square. So mass and velocity ka square is there, but I don't have a half, so I adjusted a half here and half here. So my equation turns out to be half mv CRMS squared equal to 3 by 2 PV. So this side is nothing but the kinetic energy, and 3 by 2 PV is what we got an equation. So kinetic energy of a gas is 3 by 2 PV. So this is the first form of finding out the kinetic energy. Now we will be deriving most of the kinetic energy equations from this particular equation itself. Let's see. The second form of kinetic energy is kinetic energy per unit volume. So it is as good as it gets. Kinetic energy per unit volume is just division of this equation by volume. So this is the kinetic energy of gas, 3 by 2 PV, and if I want to find out kinetic energy per unit volume, I'll divide this equation by V. So V and V get cut, I get 3 by 2 PV. So kinetic energy per unit volume is just 3 by 2 P. Okay. Now the third form of kinetic energy is kinetic energy per unit mole. So kinetic energy per unit mole, if I wish to find out, then kinetic energy of a gas is 3 by 2 PV, which we have just derived in the first part. I'll just replace PV is equal to nRT. This is our ideal gas equation. So wherever there is a PV, I'll put at nRT. So that is nRT. Now this is the kinetic energy of a gas, but I want to kinetic energy per unit mole, and if I want to find out per unit mole, I'll have to divide this equation by number of moles. So that is divided by number of moles, n and n gets cut, what remains is 3 by 2 nRT. So 3 by 2 RT, that becomes our kinetic energy per unit mole. So this is the third. Let's go to the fourth and the most important form, that is kinetic energy per unit volume. So for a molecule's kinetic energy, we again use the same the equation which we just derived here, kinetic energy per unit mole, 3 by 2 RT. So 3 by 2 RT. Now we all know that in 1 mole we have a number called as Avogadro's number of molecules. So if 1 mole consists of 6.022 into 10 raised to 23 number of molecules, then I'll just have to divide this equation by the Avogadro's numbers, because 3 by 2 RT is for Na. Na means Avogadro's number of molecules. So for this much number of molecules, this much is the kinetic energy. So what is the kinetic energy? What is the kinetic energy for 1 molecule? So just cross multiply and you get this kinetic energy per unit molecule would be 3 by 2 RT upon Na. Secondary, you can also do it like this. If I wish to find out kinetic energy per molecule, per unit molecule, I'll just have to divide this by Avogadro's numbers, because this is the kinetic energy for Avogadro's number for 1 mole. This is for 1 mole and this is for 1 molecule. Now, in my previous videos I have shown you that R is equal to Na into Kb, where Kb is called as the Boltzmann's constant. And Boltzmann constant ka value is 1.38 into 10 raised to minus 23 joule per Kelvin. So that is Boltzmann constant. Baki Na is Avogadro's number, R is universal gas constant. So in place of R, we'll write Na into Kb. So this, in place of R, we have Na into Kb. Into T upon Na and Na gets cut, and what remains is kinetic energy per unit molecule as 3 by 2 kBT. Now this is one of the equations which we are going to utilize in finding out the specific heat capacities and the ratio of specific heats in my further videos. Okay, anyway, last and the final, the fifth type of kinetic energy is kinetic energy per unit mass. So in the first part, we have seen that kinetic energy of a gas is 3 by 2 PV. PV from ideal gas equation, PV is equal to nRT. This is the ideal gas equation which transforms PV is equal to nRT. So wherever there is a PV, I have put an nRT. Now number of moles can be written by two methods. One is the number of molecules divided by the Avogadro's number, and the second is mass of gas upon the molar mass. So M0 is the molar mass of a particular gas. So wherever there is an N, I have written as M upon M0, molar mass. Now this is the kinetic energy of a gas, but if I want to find out the kinetic energy per unit mass, I'll have to divide this by mass of gas. So I have divided this by mass of gas, and M and M gets cut, so I get 3 by 2 RT by M0. So these are different forms of kinetic energies we might require in some problem solving, or maybe yes, this kinetic energy of a molecule is utilized in many aspects and different forms when coming to specific heat capacities, which will be discussed in the next lecture. So if you're following, thanks so much for following and watching all these videos. Please subscribe the channel and keep watching. More videos are going to come ahead. Thank you so much. Bye.